Just as the Hubble Space Telescope began its sensational run, several new observatories were christened on the mountains in Hawaii in the north and the Andes Mountains in the south. Two rival teams of astronomers each zeroed in on the galactic center to see what was there. These teams each undertook a multi-decade effort to track a population of stars that seemed to orbit a concentrated source of energetic emission, called Sagittarius A star. Finally, in the spring of 2002, a star labeled S2 swooped in close, accelerating to a remarkable 18 million kilometers per hour. If its path near Sagittarius A star proved erratic, astronomers would know the galactic center was packed with multiple massive objects. Instead, its path was smooth. They concluded that S2 and its companions must be orbiting a single object, weighing several million times the mass of our sun. A supermassive black hole. This effort, more than 2.5 decades after it began, was recognized with the Nobel Prize in Physics. Since that discovery, astrophysicists have been feeding additional observation data into their supercomputers to better understand how clouds of gas flow around and into the monster, and how its immense gravity drives the motions of stars at the center of our galaxy. The star S2 will inevitably return to the black hole. The pull of gravity will cause its orbit to shrink, pulling it ever closer. Astronomers recently caught a glimpse of what would then happen. A survey telescope in the Andes Mountains recorded the sudden brightening of a galaxy in distant space. Astronomers at the European Southern Observatory turned their telescopes toward the source. The light had come from a galaxy 215 million light-years away. Astronomers tracked the event through to its ultimate demise 6 months later. They deduced that a star had wandered a little too close to a supermassive black hole. The giant began to tear it apart, turning the star into a river of hot gas, fueling a high-energy jet bright enough to be detected from Earth. Astronomers have long nurtured the hope of seeing a black hole directly, to understand its properties and how it disrupts the space around it. In recent years, an international group of astronomers has been working on just such an audacious goal. Like the Eddington expeditions a century before, these scientists hope to test Einstein's theories, only this time in the most extreme laboratory the universe has to offer: a black hole. The idea was to adapt a technique developed over 60 years ago called long baseline interferometry. By synchronizing radio telescopes all around our planet, a team of 400 scientists and engineers created a much larger virtual telescope with an aperture the diameter of Earth itself. It has a resolution equivalent to being able to read a newspaper in Paris while sitting in New York. They call it the Event Horizon Telescope. Their goal: to capture the first ever image of a black hole. Their target: the monster at the center of M87. Probing deep into M87's luminous core, the astronomers struck a delicate balance between filtering out interstellar dust and finding the outlines of their quarry. At a radio wavelength of about 1 millimeter, all the dust and gas obscuring the monster faded away, leaving this ghostly silhouette: a black hole, an object that cannot, by its very nature, be seen. The Event Horizon Telescope relies on a tool that has transformed the study of the universe. To make sense of the vast amount of data captured by the many receivers, researchers developed a series of computer simulations visualizing the complexity of the scene. Here are some of the results. The dark nucleus is the event horizon, a shadow left when the object's immense gravity slows all light to a stop. The singularity, the black hole itself, is hiding in the shadows. The visible ring marks the spinning accretion disk. It's brighter on one side because the gas there is spiraling towards the telescope, its photons piling up. The light from material moving away becomes dimmer as its wavelength stretches toward the red part of the electromagnetic spectrum. From a slightly more distant perspective, you can see how a portion of the inflowing matter is flung out in a fiery, pulsating jet. M87 is a black hole of truly cosmic proportions. It has been bulking up for billions of years on a steady diet of gas, dust, planets, and stars. But it's not the only billion solar mass black hole out there, or even the largest. The Coma Cluster is a dense grouping of galaxies 321 million light-years from Earth. Its center is occupied by a colossal elliptical galaxy, cataloged as NGC 4889. It harbors a black hole estimated to be 21 billion times the mass of the Sun. J2157 is even larger. At 34 billion times the mass of the Sun, this ultramassive black hole is 8,000 times larger than the one at our Milky Way's core. The largest black hole yet spotted, TON 618, may weigh as much as 66 billion of our suns. It drives a superluminous quasar shining 140 trillion times brighter than our star. Theoretically, there is no limit to how large a black hole can grow. All it takes is time and the right circumstances. The building boom of ever larger telescope mirrors has given astronomers a whole new vantage point on the life cycle of ultramassive black holes. Here, in the high northern deserts of Chile, they have been combing the early universe for dim clues of black holes on the rise. Out in the southern constellation of Leo, they spotted the most distant quasar yet observed, just 770 million years after the Big Bang. The red dot is light energized by a black hole estimated at 2 billion times the mass of the Sun.